morning. So the last family of the well-known specialized metabolites are alkaloids. Alkaloids, you know them surely because they are very famous for several drugs that are very important in our pharmacopoeia, such quinine, for example, morphine, strychnine, that are used currently in several treatments. But also, you know, caffeine, for example, and theine was also one of the alkaloids, the most famous alkaloids. What are the common point with all of these molecules that show a very diversity of the structure? Is that in fact they have nitrogen atoms in their structure, and this nitrogen atom could be included in a ring or not. But the idea is that there was one, and here you have some of effects that can be can be used, enfin, not effect. Sorry. There is some pharmacological effect that are used in different treatment. Actually, for example, such as analgesic, anti-hyperglycemic, anti-cancer. Lots of molecules that are with anti-cancer activity come from alkaloids. Perhaps you know vincristine, vinblastine, two of very important molecules for lots of type of treatment against several type of cancer. We will have time to discuss about them. And some also have other type of effects, such as antiarrhythmic, antibacterial, and also psychotropic. Okay, if you see, such as, for example, cocaine and so on. All of these molecules may have direct effect on the health, human health. And these alkaloids, why they are so diverse, they can be classified into different classes. And this classification is based on their chemical structure. Obviously, it's a chemical molecule. And also, we can take in account their pharmacokinetic property, mainly for the those that are used as drugs. So how they have how they act in the human body, and how the time of which they are staying in the body, where, and so on. So there is a lot of known property named pharmacokinetic properties, and also because they come from plants, botanic origins may be taking count to do this classification. What we know now, it's one of the family of which we know lots of molecules, about 1,200 known molecules of alkaloids have been already described and also characterized for their potential biological activity. Then what we observe is that about 20% of the angiosperms that are able to produce some alkaloids, not the same, okay, as we have seen yesterday, they are spike-specific, molecule. And this is also interesting, is that in fact there is a scaffold with a nitrogen in a structure, but you can have addition of other type of molecules, such as steroid, secoiridoid, terpenoid, type of molecule we have seen yesterday. So in fact, alkaloids can be very, very complex molecule. This is why, in particular, it is quite difficult to obtain by a chemical synthesis. So when you have someone that are very important, the chemical synthesis is not completely impossible, but it is too long and they cost so many that it is impossible to imagine to transfer this synthesis at an industrial level. So this is why, for in particular this type of molecule, it remains the only raw material remains the plants. And we have exactly the same problem as it was discussed yesterday. The demand is increasing, but the cultivation of the plants can't be increased as much as it is necessary to have enough molecules. So it is becoming very urgent to develop several biotechnological strategy to produce this type of molecule. And after, I will share with you different examples that concern particularly these alkaloids. So what it is always the case is that allocation of precursor from primary metabolism means that the entrance in the pathway is an amino acid decarboxylase, and we will see that after. So this is all the type in the classification, all the type of alkaloids, and be sure I don't want to describe all of them, just one or two. But you can see that in fact, depending of the structure, include the nitrogen, but also eventually the link with several steroid or other molecules. They have been classified, yes, into these different classes. For today, I just want to focus on 4 families in this group. One is pyrrolizidine alkaloids, because it is one of the family in which we have already described more than 100, about 400 molecules now. Okay, and also tropan alkaloids. Lots of work have been done on this type of molecule, because some of them have a psychotropic effect very strong. They can be used as drugs, but for pharmaceutical application. And also the monoterpenindole alkaloids. You see here that in this group there is a lots of molecules that have been well described, and it is in this group that we found very, very useful anti-cancer molecules such as vincristine and vinblastine. You see 3,000 molecules have been already described, and the particularity is that all of them derive from this precursor, the streptozinine. So as we will see after, this is the main precursor of all these 3,000 molecules. And the last one, here's the group of benzylosocylcholine alkaloids. You see here also very numerous molecules have been already described. And one of the most known is morphine, that it is useful, okay, for different application in medicine. So, pyrrolizidine alkaloids derive from arginine ornithine. You see here that as a precursor, amino acid precursor. Yesterday I explained that lots of this metabolic pathway take their origin from an amino acid, here arginine. And in fact, as I said previously, the first step here, a decarboxylation of the ornithine, okay, to enter in the pathway leading to the production of several intermediates. What it is interesting is that the scaffold structure of this pyrrolizidine alkaloid is here, and the retroniceine is one of the most important intermediates, okay, leading to different, all of these different molecules. Here you have the examples, some examples, structure example of several pyrrolizidine alkaloid, and you see that there is this common structure that they share. After there is other type of ornamentation, but they have this common, okay, structure, that it is the mark, okay, of this type of alkaloids. Here are 2 examples of plants. The main family that are responsible of producing this type of alkaloid come from Boraginaceae, okay, and here it's 2 examples that there was quite funny, because in this case, for example, in Borago officinalis, there is some alkaloid, and the essential oil of this plant is so useful, but we need to avoid the alkaloid because they are very cytotoxic. So it's not for this that we use, for example, this plant. On the contrary, for example, in the same family, Symphytum officinal, which is also a boraginacea, is considered as an herbal medicine. And in this case, we use specifically some extract or some molecule, in particular alkaloids. So means that in fact, they are not all toxic or all good for the health, depend of their activity. So they need to be studied, okay, in regards of what we can do for our health, for example. But what it is true is that in the same family, all of them are able to produce some alkaloids. Propanalkaloids, this is also a very interesting classes of alkaloid. They come from mainly two big families, Solanaceae and also Linaceae. I don't know, there is a lot of examples here on Solanaceae. You have tomato and so on and so on, potatoes and so on. One of the most known is the scopolamine, that it is used also for different applications. And you see here, you have an nitrogen, but this nitrogen is included in a ring. And after there is another type of ornamentation. And what it is interesting is that all of the tropanalkaloids come from also ornithine arginine, but the main common molecules is putrescine. So it's like I showed you before, putrescine is at the origin of several sub-branches that lead to a large different molecule of this family. Perhaps the plant that it is more known to produce this type of alkaloid is Datura officinalis. Be careful if you are close to a Datura because it's very toxic, and be careful. We are normally very careful with young kids because it can be a poison for them. But we can use this poison as a drug, so for different objective, parasympatholytic, local anesthetic, treatment of digestive disorder, and also atropine in particular is used as an antidote of anticholinesterase toxin, which is, for example, found in venom of snails, for example. Okay, so that it is what we can do. Monoterpenindole alkaloids. These alkaloids, as it is written in the name, are not only alkaloids, they are combined with monoterpene moiety. Okay, we have seen yesterday what is a monoterpene, and with a group indole that includes the nitrogen molecule. These alkaloids come from the amino acid tryptophan, that it is immediately transformed in tryptamine, and the condensation between tryptamine and secologanine comes from terpene, okay, lead to the production of these common intermediates named streptozidine. And what is shown here is that this molecule is able to produce a very, very, very large amount of alkaloids. And lots of these alkaloids have several biological activities. So it is one of the most important pathway. And also, as we have some teams over the world, my team is working on these particular molecules, and we have now completely deciphered a large part of the pathway leading of a very large number of different type of alkaloids, monoterpenindole alkaloids, and every time we find some new activity of this type of molecules. So the two main plants known to produce alkaloids that are useful for several treatments are Rauwolfia serpentina and the Catharanthus roseus, namely, okay, Indian snake roots for this one, and also Madagascar periwinkle here. Both of these two plants are currently cultivated here in India because you have the perfect condition of their culture. And for example, all the alkaloids used that come from Cantharanthus roseus come from cultivation of this plant here in India. So they are very important for you, but for the world, okay, because I think it is, for the moment, it is the main source of production of this molecule. So 3,000 structures have been already characterized. They come from specifically the three family of gentiatanal, I name Procinaceae, Cantharanthus and Provolcia Procinaceae, Loganiaceae and Rubiaceae. But there is also some ancestral plants that may produce some of these alkaloids, which is very interesting to compare, for example, the pathway between this ancestral plant and this more modern one to understand what are the reason of this diversity, molecular diversity of this alkaloid. And okay, tryptophan is an amino acid indole precursor. And to finish, okay, I would like just to have a slide on benzyl zoquinolene alkaloids, and that you see they share a benzyl zoquinolide. It's quite difficult to pronounce sometimes. Okay, structure. This is the structure, and in fact, you see that from this very simple scaffold, you can have a very big, large diversity of structure that lead to a very large family, more than 2,600 compounds have been already described. Perhaps the most plant used and studied for this type of alkaloid are Papaver somniferum, because I think it is like Cantharanthus, one of the most known pathway that permit to understand how this molecule can be produced by plants. Okay, so this is the three main classes that perhaps you need to have a little more some idea. But just to finish, alkaloids can be also divided in three categories. The first one is the true alkaloids, such as I show you immediately. But we can observe that if the common property is to have include nitrogen in the structure, there is also other type of molecules that have nitrogen included in their structure. So how we can do the difference between alkaloids and other molecules? It can be very hard sometimes. So this is why there is two other type of classes of alkaloids that are named photoalkaloids. What is the particularity of this one? They're derived from amino acid, but in fact, what happens? The nitrogen is not included in a heterocycle cycle. It's mainly an amine function that have this nitrogen. So it was, sometimes they have the same activity as true alkaloids. This is why we admit to have some similarity with these two types of molecules. And also a third class, which is named pseudo-alkaloids. These classes have don't derivate from an amino acid. Tryptophan, for example, as I show you for MEA. And in fact, they derived from terpenes, sterols, aliphatic acid, nicotinic acid, and so on and so on. And in this category, you can find, for example, caffeine, that it is one of example of this pseudo-alkaloids. So it's just to show you that it is not so easy to characterize every time each molecule as a molecule of alkaloid groups or not, and depend of several properties, but also depend of the pathway that lead to this the biosynthesis of this molecule. So it's always important to have this idea. And here I propose you, I don't want to read the whole, but I propose you a table that summarize, okay, some of very known alkaloid that have been qualified of true protoalkaloid or pseudoalkaloid. Here are the chemical group of the alkaloids and also the amino precursor, when there is one, okay, of this molecule. So you could take time to see and to read all of these two tables that can give you some idea of which are this type of molecules that are included in this type of, in this group. I'm sure that if you read this list, you could have some molecule that you have heard about during your lecture and during also what you different articles in journals and so on. And to finish, this is a part of the pathway. I will discuss this just after. But you can see here that from as you see, always the same thing, photosynthesis, glucose production. And from this one, you have here the 3 amino acids, aspartate, arginine, tryptophan, and tyrosine, that are the initial point of production of this type of alkaloids. For example, we have seen that arginine by putrescine intermediates lead to pyrosinidine alkaloid and tropane alkaloids. And tryptophan, we have just discussed about this, lead to monoterpene alkaloids, while tyrosine lead to quinoline alkaloids. And the third group, I didn't spoke about it, but it doesn't matter, is quinolizidine alkaloid, but it is also known to have a common intermediate that is considered the precursor of the alkaloid, is cadaverine. These alkaloids gave a very bad savor and odor, of some of the flowers that are producing these molecules or the plants. So here it's very interesting because with this picture, we can see that are very closed, from the one from the others, but they have some very different particularity. And it is really a challenge to produce this type of molecule for several applications. And to finish also, this is what I want to show you. We have seen that, for example, for pyrolizidinic alkaloid, we have this structure that is common to all of the members of this family. Also for MEA, monoterpene indole alkaloid, it is an indole group that comes from tryptophan, that it is the base of the scaffold of the tropane, it is this one, and so on. So someone asked me the question to see when we have a molecule, how we can know that what type of metabolite it is, and in what category we can classify this molecule. In fact, now there is some identity, chemical identity of specific part that can permit to classify the molecule in one or in another class of alkaloids. Is it okay for all of you? And I have also introduced this table that is a way for you to have an idea of the pharmaceutical industry and medical support used of this particular molecule. Here are the alkaloids, here the plant sources, so means that you can see that we see Papaver somniferum here, Catharanthus here, Revolvia here, for example, and this is the current use of this molecule in our pharmaceutical application. And for all of them, it can be difficult to have enough molecule considering the demand that it is increasing. So it's really a challenge for that. Because what happens is that we can't increase the fields, the surface used for their cultivation, because they are in competition with a plant for food. So we need to find, some compromise situation between plants for food and plants for pharmaceuticals. For this part. And the second part I wanted to discuss with you is this one, because biosynthetic pathway leading to this type of molecule are very complex pathway. In general, it is not only 1, 2, or 3 steps. You have seen just by my last slide that in fact there is lots of step and lots of branch, sub-branch, and so on. So it's really a complex system of this metabolic pathway. But fortunately, I can say that's like that. Each step, each biochemical bioconversion are catalyzed by specific enzyme. And in fact, when we take a look of all the metabolic pathways that have been already described and already characterized, we can see that there is some specific enzyme family that act in all of these pathways. So it's very interesting because by this way, we have a short number of this enzyme family that are really involved in this pathway. So when we wanted to develop some bioengineered process, the main target we have are this enzyme, because with one enzyme, you can have a specific modification. And as the number of the family is quite limited, it's easier, okay, to anticipate which type of enzyme could make this type of chemical modification. The problem is that in each family, there is not only 1 or 2 or 3 genes that encode for this enzyme, but several hundred of genes for all of them, which is a more complex situation. So before to shift to the metabolic pathway and their organization, I wanted to introduce you, okay, the specific families of enzymes that are really more involved in metabolisms. Okay, just to share with you the idea of how it is organized a metabolic pathway leading to specialized metabolites. As we have started to see, there is a first part, okay, that involve primary metabolism that lead to first the precursor, mainly an amino acid. This type of metabolism is completely common to every plant, because these precursors are also precursors for several other primary metabolites. So this is not a specific part of the pathway. Generally, these pathways are very well known. There is no problem of having an idea of each step of this pathway. What it is interesting is that, in fact, they lead to the production of what we call a first intermediate that is common to several plants, mainly by family, okay? And this first intermediate can be taken charge by several enzymes to lead to a second intermediate. Difference between this part of the metabolic pathway with this one is that if this one is general to all plants, this second part is common only to a smaller numerous of plants. Mainly, they are conserved in a family, for example, or in a clade. So this is more strict, okay, to a specific, for example, like Boraginaceae or these others that are able to produce several intermediates. For example, for the alkaloids of monoterpeninol alkaloid, streptozidine is considered as this second, okay, metabolite intermediate. And after, there is a third part of this pathway that are really specialized. Sometimes they are unique. This part is unique in a plant, in a specific species. And this is what we are looking for, because we wanted to know how these second intermediates can lead to the production of a specialized metabolite. So this is the main point when we want to decipher completely a metabolic pathway. And what we see is that, in fact, a large number of these metabolites exist, okay, in the plant kingdom, but only finalement few major pathways lead to their biosynthesis. What I want to propose you today is not only to see the enzymes, but also how this pathway generally, okay, are considered. Because by this way, it is easier for us to try to find some branch or sub-branch that are completely unknown today. So it is exactly what I explained here. The intermediates concern the first different type of scaffold, okay? And after you have some modification of this scaffold that is achieved by different enzyme activity that include carboxylation, oxidation, hydration, and so on and so on. And I propose you to see this type of molecule. And what it is true is that more you have a bigger diversity, molecular diversity at this level than this one. Okay. All of this modification leading to this specialized metabolite. Here, for example, it is represented at least 4 type of modifications, such as hydroxylation, methylation, glycosylation, and acylation. Hydroxylation is the addition of hydroxyl group OH on the molecule. Methylation is the addition of a methyl group, a carbon, okay, with hydrogen. It is, for example, here. And glycosylation, you understand, it is the addition of a sugar. Not only glucose, it can be also rhamnose, whatever sugar can be added. It is, for example, shown here, here, and here. And acylation, it's a specific activity that occurs generally at the end, completely the last steps of the metabolic pathway, and that permits to construct very complex structure, sharing, okay, just to make the assembly, to build, okay, with 2 big systems, so big structure, a bigger one, okay. It's generally more complex than glycosylation, methylation, or hydroxylation. Both of these 4 main activities are the fact of specific enzymes.